Okay, so I was telling you that the calculus teacher was saying that her students were having a hard time seeing this, but you guys are all seeing it very clearly. The exponential one does a log one does an exponential. Then remember there are special exponential functions, e to the x, which is just an exponential, right, with a special base, and one of that is the natural log. Okay, so base 3 and log to the base 3 you said canceled out. Oopsies. Canceled out. So I saw that all of you put 10. Very good. It should be that quick. So then right here, ln and e undo each other. They're inverses of each other, so they undo each other, so we get 2. All of you were able to see that pretty quickly. Okay, questions on that? Real quick on some things that we learned last time. So we just talked about it. An exponential is the inverse of a log, and the log is the inverse of an exponential. So if I said to you, take this true statement and rewrite it as a log, this is base 5 to the third power. So we would do log to the base 5 of both sides of the equation. So then they cancel out. So we would have 3 is equal to log to the base 5 of 125. Right, everybody? Okay. Then over here, if I said to you, write this logarithm as an exponential, you would say, okay, base 16 of both sides, right? That one does that. 8 is equal to 16 raised to the 3/4 power. Then it should be a true statement. So, and it is. Remember, this means the 4th root of 16 to the 3rd power, if we wanted to get technical, and we could simplify that. Or we could also type it into our calculator, but yeah. All right, so ln of 4 equals 1.386. Notice we're not solving anything, it's just rewriting it as an exponential. So E undoes ln. So we have 4 is equal to e raised to the 1.386. We've just rewritten it as an exponential. If we want to do e and rewrite it as a log, we would do ln of both sides. So 2 is equal to ln of 7.3. All right. So recall, log to the base 10 will have the form y is equal log of x, right, everybody? Right. Wait a minute. I swear I want to go over. Hold on. Just a second. So guys, I want to go over something real quick. So I wanted to go over this before we get started on today's lesson. So last time we were asked to graph this. I want to make sure that you can answer these questions without graphing though. So I didn't hit very hard on that last time, but we really, really need to be able to answer these 3 questions without graphing it, and then also being able to graph it. So if I give you this, y is equal to log to the base 3 of negative 2x plus 4, and I asked you for the vertical asymptote. Let's think about this, guys. Log to the base 3 would be the parent function. Log to the base 3 of x would be the parent function of this, correct? And then wouldn't we have a horizontal asymptote at 0? It looks something like this, correct? Okay, so we'd have a horizontal asymptote at 0. So now if we take and shift it left or right, that's going to change our asymptote, isn't it? Okay, so let's just figure out the vertical. So to figure out the vertical asymptote, let's figure out our shift left and right. Isn't that always what's grouped in with x? And you go opposite. Well, notice there's a 2 in front. So we're going to do some algebra. So we're going to say negative 2x plus 4 used to be equal to 0, but now it's shifted, right? It used to just be x equals 0, but now we're shifting it. So let's solve for x. So we subtract 4, negative 2x equals negative 4. We divide by negative 2. So x equals 2. So our new asymptote, our new vertical asymptote is going to be at 2. Does everybody understand? So our vertical asymptote is at x equals 2. Okay, our x-intercept. You want to be able to do that with just algebra. So for all functions, guys, the x-intercept is when y equals 0. So let's set up our true statement. 0 is equal to log to the base 3 of negative 2x plus 4. Now solve for x. So what do we need to do? It's trapped inside log to the base 3. How do we undo log to the base 3? Base 3 of both sides. What's 3 to the 0 power? So we have 1 is equal to base 3 and log of the base 3 cancel out, negative 2x plus 4. Now solve for x. So we'd subtract 4, right? So we would have negative 3 equals negative 2x, right? Subtract 4, divide by negative 2, so x is equal to 3/2, right? Positive 3/2. So our x-intercept was 3/2, comma 0. So that's over 1.5, comma 0. and that's where it's crossing the x-axis. Now our domain, we want to just use algebra. We could graph it and then do domain, but we don't want to have to graph it. So don't we know that a non-shifted function's domain would be 0? It's got to be greater than 0, not equal to 0. That's the important thing. Isn't our domain for a non-shifted function x value is greater than 0? Yeah. Right, everybody? Yeah. You're going to use this in calculus all the time. Okay, so now, isn't it true since it's shifted, you're going to be able to just set up an equation and say negative 2x plus 4 must be greater than 0, correct? Yeah. You see what I'm saying? I'm just setting myself up an equation. Now when we solve, it'll find the new, it's like the new asymptote, just like we already did, kind of. But an inequality we have to be careful with. We can't just treat it like an equal sign. I mean, kind of, but we just got to be careful. So let's solve for x. Like we've already done, subtract 4 from both sides. So negative 2x is greater than negative 4. Divide both sides by negative 2. When you divide by a negative, you have to switch the sign of the inequality, right? So we have x is less than 2. X value is less than 2. So our domain is x value is less than 2, or negative infinity up to 2, not including 2. Now that makes sense if you think about what the graph is going to look like, because remember, there are two types of shifts. There are two types of reflections. A reflection over the x-axis, which would look like this, negative log the base 3 of x. And there's a reflection over the y-axis, which we haven't seen in a while, which would look like this, log to the base 3 of negative x, right? Plugging in a negative x as a reflection over the y-axis. So do you see how we have a negative plugged in front of x? So that's going to take and reflect this over the y-axis. So it's going to look like this instead. So look at our domain. Does it make sense? Our algebra came out. X value is less than 2. Isn't that what we're looking at here when we graph this? Yes. Yep. Okay, everybody good with that? Yeah. Okay, awesome. Okay, so now we can get started. Sorry about that. Okay, so recall that log the base 10 will have the form y is equal log of nothing to the x. So that really is a base 10 in there, a secret base 10 in there. Okay, so this is not always true. Some of your calculators are advanced calculators. However, you still need to be able to do the change of base formula. Here's why. Because I literally learned calculus 1, 2, and 3 without so much as even touching a calculator. So when you do calculus, there's a good chance you're not going to be able to use these schmancy calculators to just do it all for you. So even if your calculator does it for you, what I'm about to teach you, you have to learn it this way still. You have to understand this still, okay? So everybody pay attention. Okay, so most calculators, like for example, my TI-83, this little guy, most calculators have only 2 types of logarithms that they can actually calculate. So they have log to the base 10, so everybody pull up your calculator. So notice this calculator has, over here, we have log to the base 10. So we just have log. Let's get out of here. So look, if I type in log, do you see how it's log to the base 10 automatically? It's not log to the base 3, it's not log to the base 5, it's log to the base 10. So we can only calculate log to the base 10 in our calculator. For example, log to the base 10 of 2. So, also we have this ln, which is our natural log. So most calculators only have 2 types of logs you can calculate. So what happens when we have something that's not base 10? We still have to be able to calculate it with our calculator. So this is a way, the change of base formula is a way to take any logarithm to any base and rewrite it in base 10 form so that you can use your calculator. So once again, we can take any logarithm to any base and rewrite it as base 10 by using the change of base formula. So here's the change of base formula. If you have log to the base a of x, I'm going to put parentheses around x. This is really this, if you want to be technical, log to the base a of x. You can rewrite it in base 10 by taking the log of base 10 of x divided by log of base 10 of a. You see how they did log of x over log of a? So you can do that. It's just the change of base formula. They're equal, different forms. You can also use, instead of using log, you can use ln. Same thing. So log of base a, log of x over log of a. So they're base 10. So there's technically a 10 in there, but it's not going to be written. So this is just a little trick I use to help myself remember that. So you know how this is smaller in size? Not smaller in number, but smaller in size, this little mini a? Smaller, do you get what I'm saying? Smaller in size. You do log of the big thing divided by log of the small thing. But that's in size, not number. Does that make sense? This is mini. So if this is 25, it's still mini. Like written as a mini little a. Do you get what I'm saying? Yeah. So log of 25 of 5. You see how 5 is larger in size? Yeah. Log of 5 divided by log of 25. It's just a trick that you can use to help remember. So it works because technically we're going through and we're changing it by, how are we? Let's see. Yeah, sorry about that. Let me scroll up. So watch for a second and then I'll show you why it works. I really will. I'll come back to it. So everybody, if I click this, log of the base 25. So once I remind you of what this means, we'll see why the change of base formula works here, okay? So remember what this really means, log of the base 25. We can go ahead and rewrite it as an exponential. So let's do that. So remember last time we were doing this, right? If I said to evaluate that, we could try rewriting it as an exponential and evaluating it that way. So we don't know what it's equal to, so I called it equal to x, right? This is what we did last time. Yeah. So then to undo log to the base 4 so that we can rewrite it as an exponential, because it's easier to evaluate an exponential sometimes, we did base 4 of both sides. So we have 25 is equal to base 4 raised to the x power. Now, is there any power, straightforward power, that will give us 25 if we plug it in for x? No. So do you see how this didn't really help us? Like, it's some decimal, we're not going to ever be able to just guess. Does that make sense? So that's why we use the change of base formula, because it's like very straightforward. Like, you can always get the answer. So watch how it works, and then we'll see why we can do this. So let's do it using the change of base formula instead, because this didn't help us. So we can rewrite this as log of 25 divided by log of 4. That's just putting it in the same base, base 10. Yeah. Okay. So I was just trying to think of how I could explain. So everybody type that into your calculator. Go. So you'll type in log of 25 divided by log of 4. Log of 25. Oopsies. So log of 25, close your parentheses, divided by log of 4. So we get this decimal, this very long decimal, correct? That is our answer. Now watch, I can even check to make sure that is truly my answer. Didn't we rewrite this as an exponential? 4 to the x power equals 25. So there's our x power, that huge decimal. Let's type it in and check it. 4 to the... I'm going to hit second answer so I don't have to retype the whole decimal. And I hit enter, and look at that. It really is 25. So we would have never guessed using exponentials. You know what I mean? Okay. So the change of base formula allows us to just solve it very quickly, getting it in base 10. Now, we could also rewrite it as ln. So ln of 25 divided by ln of 4. That's fine as well. It'll come out the same decimal. So ln of 25 divided by ln of 4. And we get that same decimal. So either way will work. So look at this one. It's the same idea. If we have log to the base 2 of 12, I tried to solve it. I tried to evaluate it or simplify it by rewriting it as an exponential. 2 to the x power equals 12. So that's what this means, right? Log to the base 2 of 12 means what base 2 to what power equals 12? Well, nothing that I can think of, nothing pretty. We don't have a pretty answer is what I like to say. We would use this formula here. So you can type in log of 12 divided by log of 2. We can also type in ln of 12 divided by ln of 2. What's the decimal? 2 raised to the 3, so it was what? Can you tell me the whole decimal? 3.849. Oh my, I'm confused. What's 5? 3.8. Okay, 3.58. Perfect, that's our answer. So that full decimal. So if we were gonna check it, guys, and a lot of times they'll say round to the nearest, everybody listen, they'll say round to the nearest 3 decimal places or whatever. But if you're gonna check it, you're gonna wanna type in the full decimal. So it comes out perfectly. Okay, perfect. So now we're on to properties of logarithms. Okay, so guys, everybody listen, because then this is really not new to us. So you're gonna wanna write this down or take a picture. We know that logarithms are inverses of exponentials, and exponentials are inverses of logarithms. So what I want you to think about is properties of exponents. So I'm going to insert a blank page after you guys get a picture of this. Properties of logs. I want you to remember properties of exponents. If we have base 2, if we have base 2 to the third power times base 2 to the x power, for example, when you multiply the same base, what do you do with your exponents? You add them. So this is the same thing as 2 raised to the x plus 3, or 3 plus x, right, everybody? So then also, when you divide, you subtract. When you divide the same base, you subtract. Always the top from bottom, right? So 2 to the 3 minus x, right? So we could go backwards. We could rewrite this as this, right? And then when you raise a power to a power, so 2 raised to the third raised to the x, we raise a power to a power and we multiply, right? 2 to the 3x. Okay, so properties of exponents go hand in hand with properties of logs because they're inverses of each other. So here's the product property of logarithms. If you have log to the base a of u times v, when you multiply, you add. You can split this apart and rewrite this as 2 separate logarithms with the same base. So log to the base a of u times v can be rewritten as log to the base a of u plus log the base a of v. When you multiply, you add. Now really, the more beneficial thing is to go backwards. So really what we're going to be wanting to do eventually is be able to take this and go backwards to make it 1 log. And then that works for ln as well. So ln of u times v equals ln of u plus v. And we want to be able to go backwards. So log of base a of u divided by v can be split apart and written as log of base a of u minus log of base a of v. Notice it's u minus v, the top minus the bottom. Everybody seeing the relationship here. Same with ln. And then log to the base a of u raised to the n power, raising something to a power, and you multiply the power. So we're taking this power and we're multiplying it to our log. So basically we're taking the n and putting it out front here and multiplying. So once again, really it's being able to go backwards. You see that it's subtraction, you know that you will as 1 logarithm but with division. And if you see this n in front, you know it's really an exponent. That's your goal, is to get it so it's just 1 logarithm, really, essentially. We're going to practice splitting back and forth because usually we teach this first, learning how to split apart so that it's easier once you start putting them back together. So let's start out with that. Are you guys ready? Not yet? Okay, so people on 80 say, so what is the point of this? I'll explain the point of this right now. So eventually our goal is to be able to take and solve logarithmic equations. Now, some of these logarithmic equations are going to contain multiple logs all split apart. To be able to undo a logarithm, you have to have just 1 log. So we would have to combine the logs using properties of logarithms. And then once we have 1 log, we could undo log to the base a by doing base a of both sides. You get what I'm saying, everybody? Okay, awesome. Here we go. So it says, write in terms of ln of 2 or ln of 3. So just look at the instructions here. It says, given the ln, write it in terms of ln of 2 or ln of 3. So instead of ln of 6, it needs to be in terms of ln of 2 or 3. So how can we rewrite 6 as 2 and 3? ln of 2 times 3, correct, everybody? Okay, so 6 is the same thing. This is literally equal to this. So now what we're going to do is split it apart. When you multiply, you add. So we can split this apart and write it as 2 separate ln's. ln of 2 plus ln of 3. So now the goal would be going backwards, really, essentially. Because yes, I get, you're like, why do that? But it's doing this to prepare you to be able to go backwards, okay? So looking at this one, ln of 2 divided by 27, the instructions are write each in terms of ln of 2 or ln of 3. So how can we rewrite this? ln of 2 divided by, very good, 27 is 3 to the third power, okay? Now let's split it apart. So we have ln of 2. When you divide, then you subtract. So minus ln of 3 to the third power, right? So now what we're going to do is we're going to take our exponent and pull it out in front, raising something to a power, and you multiply the power in front. So this is ln of 2 minus 3. The exponent comes in front and multiplies to the ln of 3. So this would be splitting it apart in terms of 2 and 3. Questions? Okay. Okay, so it says find the exact value without using a calculator. So guys, to be able to do this, you're going to want to have one logarithm. So everybody look at this. Log the base 5 of the cube root of 5. So right now, we know that log the base 5 and base 5 technically cancel out, right? But this is the cube root of 5. So let's rewrite it. So let's rewrite it with exponents instead of radicals. So this is log to the base 5 of 5 to the what power? 1/3. And now look, you have log to the base 5 of base 5, right? So it cancels out, so we get 1/3. That's simplified to be 1/3 without using a calculator. Okay, now looking at this one, there's two ways to simplify it. We can either combine our ln's, right, using properties of ln's, or can't we see right here that ln and e undo each other? So ln and e undo each other, so this piece becomes a 6, minus ln and e undo each other, so 6 minus 2, which is 4. Do you see how we're doing this here? Now really, we could have done it this way. This is a little bit longer of a process. ln. So we could put the ln's together. So ln of e to the 6, when you divide, then you subtract, or when you subtract, you divide. So e to the 6 over e to the second. Now when you divide the same base, you subtract your exponents. So ln of e to the 4th, and then ln and e cancel out, so we get 4. Two different ways of getting it. Okay, let's start expanding the logarithm. Here we go. So it says expand the logarithm. If you want to write this down, you can. So one thing to note here is log the base 4 of all this stuff. Log the base 4 of all this stuff. So they're all base 4. Now understand 5 is its own base. It's not connected to x cubed and it's not connected to y. When you multiply, you add. So we can split this apart, and anything that's being multiplied will be split apart by addition. So this is the same thing as log to the base 4 of 5 plus log to the base 4 of x cubed plus log to the base 4 of y. Now this is still not considered expanded if there's any exponents still left up. So notice we have a 3 up here, so this needs to come down in front. So our final answer would be to expand it completely, log the base 4 of 5 plus 3 log to the base 4 of x plus log to the base 4 of y. So now the goal is so that now that you see how it was split apart, it's more beneficial to take something like this and put it back together. Does everybody see how that would work? You take this, put it in the exponent, and then multiply the rest. Okay. Let's do this one. It says expand the logarithm. So notice, anytime you have radicals, you're going to want to rewrite them as rational exponents, because with logs, you're going to put those exponents in front. So you're going to put any exponent in front of the log. So let's rewrite this one. This is really ln of 3x minus 5 to the 1/2 power, correct? Yeah. Divided by 7. So now we can split it up. So we have ln of 3x minus 5 to the 1/2 power, right? When you divide, then you subtract. So minus ln of 7. And now what we're going to do is pull the 1/2 out in front here. So we have 1/2 ln of 3x minus 5 minus ln of 7. Now let me show you, we can't keep going here. This is not, you can't keep splitting that apart. That's a common mistake. People think you can split that apart. There wasn't a rule for subtraction, right? Splitting it apart. Okay. Awesome. So this would be our final answer. Yes.
Do you want it in that answer, or would you want it in that?
Well, this one asked us, it was, you mean in this form? This one asked us to expand. So we're going backwards. So if we put it, yeah.
Oh.
Okay, so now let's go the other way. This is really the goal here, to be able to take something that's split apart and put it into one logarithm. So we can use logarithm. So here we go. It says condense the logarithm. So don't we need to, this 1/2 is being multiplied in front, so that's really an exponent, isn't it?
Yes.
And look, this 3 is being multiplied in front, so that's really an exponent. So let's rewrite what we have here. Log of x, now it's base 10, right? We're not going to write base 10, but that is base 10, right? So log of x to the 1/2 power plus log to the base 10 of x plus 1 to the 3rd power. So now our goal is to put it as one logarithm, because then you can undo the log, which we're not going to undo because we're not solving, but that's going to be the next lesson. So now when you multiply, you add. So when you add, you multiply, right? So we're going to rewrite this since they're both log to the base 10. We can put this as one log to the base 10, and it's going to be x to the 1/2 times x plus 1 to the 3rd power. Now, anytime we have a fractional exponent, you will want to rewrite it as a radical as your final answer. So our last step would be saying log of the square root of x times x plus 1 to the 3rd power. So that's all trapped inside the log now. That would be our final answer. Now understand, why would that be beneficial? Because let's pretend that in the future, and we will next lesson, let's say that this was an equation and it was equal to 10. Now solving for x, wouldn't we need to undo the log? So now that we have one logarithm, we can undo it very easily. That would be 10 to the 10th power. Log the base 10 and base 10 cancel out. You get what I'm saying? So now we can solve for x. But that's not what we're doing this time. I'm just making sure you guys see like where we're going with it. Okay, just a couple more. You're going to have tons of time to get tons of homework done in class. Stay with me. Condense the logarithm. So we have a 2 being multiplied in front. So that must be an exponent. Notice they're both ln's. So ln of x plus 2 to the 2nd power minus ln of x. When you subtract, then when you divide, then you subtract. So when you subtract, then you divide. So we can now rewrite this as 1 ln. This is going to be on top, right? So ln of x plus 2 squared divided by x. So now we've rewritten that as 1 ln. That's our final answer. Now, let's pretend I said this equal to 3 and said solve. How would you undo ln? E both sides, right? And then you could continue solving for x. Okay. That's not what we're doing now. Just making sure. Okay, watching a few more. We're almost done. Condense the logarithm. So notice 1/3 is multiplied in front, right? So look, we're going to take this up, and it's going to be up here in both. So it's up here technically, right? Okay, so I'm going to kind of work from the inside out, though. I'm going to first focus in on this and simplify this first. Log the base 2, log the base 2. Now understand, you cannot combine log the base 2 and log the base 3. That's not properties of exponents. Just like you can't do 2 to the x times 3 to the first. You know what I mean, everybody? You can't put those together, so same with logs. Okay, here we go. So when you add, you multiply. So this is log to the base 2 of x times x plus 1, right?
Yeah.
So we really have this, 1/3 times all that stuff. So now, yes, we'll take the 1/3 and put it up here in the exponent. So that's log to the base 2 of x times x plus 1 to the 1/3 power. So now we would rewrite it as a radical, right? 1/3 means cube root. So our last step would be to say this is really log to the base 2 of the cube root of x times x plus 1. That would be our final answer here. Yes. You know, I would accept, no, this is exactly the same thing, so I would absolutely accept if you make sure that you distribute correctly. But if this was like 1/2, you wouldn't do that, right?
Yeah.
Okay, x squared plus x, this is just as acceptable. But you really should just be able, I mean, just stop there. Okay, so this is why I added these two on, yes? Yeah. Because remember that this 1/3, right, just like if the 2 was in front, like if there was a 2 here, this is really just exponent of that. Good question, yeah. Okay, so everybody, this is 18 out of the book. The reason I added these on is because after 8A, after I taught 8A and they started working on the homework, they really kind of struggled with this section. The instructions aren't super clear. So here we go. I'm going to show you some examples so that when you get to the homework, you're good. So it says, let's go to your book. Page 244. I want you to read the actual instructions because they're not very clear, I don't think. So in the book it says, simplify using properties of logarithms, but they're not super clear. They want you to keep your answers as like log of 2 minus log of 3. They don't want the decimal answers, you know what I mean? They don't want you to actually go through and like calculate it all. So everybody, let's use properties of logs to like simplify this. So what your book's wanting you to do is like expand it out. Completely. Okay, 243. Oh, you're good. So let's go ahead and simplify this. So this is log to the base 2 of 4 to the second power, right? Plus, because when you multiply you add, log to the base 2 of 3 to the 4th. Now what the book is doing is we're taking, obviously, this is what we would always do. Take our exponent, put it down in front. So this is the same thing as this. 2 log to the base 2 of 4 plus 4 log to the base 2 of 3. Right, yes.
Can you simplify that even more?
Yep.
Okay.
Yes, so that's, I think, what they're wanting us to go is even further, because isn't 4 2 times 2? Right? So what I think in the book, and I'm going to look at my teacher, and I know for a fact they're going further with this. Because 4 is 2 times 2. You get what I'm saying? So this is really, we have to be careful though, because this is really 2 times log to the base 2 of 2 times 2, right? And then plus 4 log to the base 2 of 3. So now when you multiply, you add. I think you just guessed and ended up with the last one. Yeah, you did. Right? Okay. So we would keep going with this. This is 2 times, let's split this up, log to the base 2 of 2, right? Plus log to the base 2 of 2, parentheses, right?
Right.
Plus 4 log to the base 2 of 3. Now think about the 2. I need to distribute here and here. So we really have 2 log to the base 2 of 2 plus 2 log to the base 2 of 2. Plus 4 log to the base 2 of 3. Let's see if we can keep going with it. Can we keep going?
Yeah.
How many log to the base 2 of 2's do we have?
4.
4. So I think your book's going to say 4 log to the base 2 of 2 plus 4 log to the base 2 of 3. Oh yeah, you know what? Let's look. Does it keep simplifying? Yes. Ding ding. You probably could have done that back up further. We could have done that back up further. So this simplifies to be 4 plus 4 log to the base 2 of 3. So do you see how like it's just simplifying it completely? Looking at it, seeing how you could go. So there are long ways and we did it right, but we did it the long way, which is okay. Yes? Huh? Which one? So there's so many ways to do this. Well, we always put exponents down in front. That's a rule. But like, do you see how what Zach is saying? Like Zach right here, isn't 4 2 squared?
Yeah.
Like 4 is there's many ways we could have done this. So now look, log of base 2 and base 2 cancel out. So 2 to the second is 4. So do you see how we could have got there much quicker? But it's okay, because It's all in, there are right ways and there are long ways. We did the long way, yes. Okay, let's do 20. Okay, here we go. So watch, that's why this is confusing, because it's like, what is it really asking us? It's asking us to simplify it completely. So let's go through this. Now, there are many ways to do this, understand. So we have log of 9 over 300. You can literally take 9 divided by 300 and then simplify first and then keep going if you want. How many of you want to do that? Sure, why not? What's 9 divided by 300 simplify to be? Yep, log of 3 over 100. That's not the only way of doing this. There are many ways of tackling it. That's what makes it hard. You have to think. Like, no. We got to keep going. So now, when you divide, then you subtract. So this is log of 3 minus log of 100, right? So now log of 3, nothing simplifies more with that one. So we know we're good there. So we have log of 3 minus log of 10 to the what power? Second. Now look, log of the base 10 and base 10 cancel out. So we have log of 3, that's not base 3, I wrote that a little bit small, minus 2. You see how that simplifies? There was other ways we could have done it. We could have done 10 times 10, and then we could have gotten that and split it apart, and then we would have had 1 plus 1. 2. There's so many ways. That's why there's not one right way of doing it. But do you see how we know we're done? Because there's nothing more we can do with 3. It's a prime, and then we simplified it to just a whole number. Okay. Do you want me to do one more? Okay, and then the rest of the time's yours. Yeah, how about you try doing this one? How about? Now, you don't have to do it the same way as your neighbor. There's like a few different ways you could do this. Like many different ways, to be honest. Okay, here is the homework problems. Ready, set, go. The rest of the time's yours, so you get as many done in class as possible because, hey, it seems like a lot, and it is, but it's because I'm giving you now 40 minutes of my class time to do it.